Okay, so we just did an example of flipping coins using the random function in Excel. So now we want to extend those random deviates to using the normal distribution, because it's pretty rare we actually see uniform distribution. Normal or bell curve data is more typical. And so we want to simulate draws from a normal distribution. So the way we'll do that is to use the norm inverse function, which accepts 3 arguments. It wants a probability, which we will select randomly using the rand function, and then a mean and standard deviation. So this is going to dictate the parameters of the distribution. So for example, if we know that say comment scores average 6.2 out of 7 with a standard deviation of 0.3, then we would put 6.2 and as the average and 0.3 as the standard deviation of our norm inverse function, and then randomly choose probabilities between 0 and 1 to represent draws from that distribution. So let's just see how that works in Excel. You do norm inverse rand, and let's see if we pick a number between, if we've got say an average of 23 with a standard deviation of 3, it should be that roughly 95% of our data is within 2 standard deviations plus or minus. So if I do this, now I've got this, and I'll go 100 data points here. I'll put that theory to the test. So if my 100 data points, I can say if this is bigger than 23 plus 6, give me a true. Oh wait, let's see. So we want it to be bigger. We need an OR here. So OR this is bigger than 29, or this is smaller than 23 minus 6, 17. Then we want, if that's true, then we want to say we're outside the range, otherwise we're inside the range. So this one's inside. Let's see, that 29 is not. As we go down, that 29 also is not, as is this 31. So we can actually count, figure out the average here. So 97, 94, 95, 96. So just in terms of whether the bell curve does have 95% of the data between plus or minus 2 standard deviations, that's what we're observing. So on their left here are simulated random draws from a normal distribution with mean 23 and standard deviation 3. And this is an if cell that checks whether or not we're within 2 standard deviations. So that's a normal draw, and that's what's going to be helpful in many cases for simulating real business phenomena. So suppose we knew a project took 20 hours on average with a standard deviation of 3. What's the chance we'll get it done in 19 hours? So our method is to do random draws from that distribution with mean 20 and standard deviation 3, and then count how many times we get it done in 19 hours and use that as a probability estimate. So I'm going to delete all of this work. So rather than having a mean of 23, we want to have a mean of 20 with standard deviation 3. So mean of 20 with standard deviation 3. So here's an example of one where we didn't get done in 19 hours. So if this is greater than, if we got it done, great, otherwise we didn't finish, right? So if that's, okay, hold on, oh, okay. So we see there, so we finished, we didn't finish, we didn't finish, we finished, just barely. And we're going to do 10,000 rows. So I'll just let it cruise down there. So once you've got your required number of simulation rows, it's helpful sometimes to hit the delete or type a little bit just to refresh the random draw and try to get an eyeball average, because every time you push to delete, it's going to effectively double, or double compared to just one run, the number of observations you have in your sample. So let's go to 5,000. That should be enough. Right, and then we need the average of all of that. So we've got 36%, 36, 38, 37, 36, 37, 36, 37. So you can kind of see that eyeball average. If you wanted to be really specific, you could just push it 10 times and do an actual average. But it looks like we're something like in the high 36s, because we see some 5s and we see some 8s. So it's probably in the high 36%. So the true answer is 36.9%. So we didn't do too bad. Okay, so now that's great. Now this 20 and 3 we could have done using the direct method because it's fairly simple, but that's not always the case. So what if we have something a little more complicated, where it's actually two tasks? You have a task with a mean of 10 and a standard deviation of 2, and a different task with a standard deviation of 2.236 and an average of 10. When you add those two together, you get a new task that has an unknown distribution, but we can check whether the total comes in under 19 by simply adding the result of a draw. Right, so we draw randomly from the first and draw randomly from the second, add them together, and check whether it comes in under 19. So you should do it. So give it a shot. Try to do a 10 average and another 10 average with those standard deviations and find the percentage of time you can finish both tasks in under 19 minutes. So give it a shot after pausing the movie and then come back and report. Okay, let's take a look and see how we did it. So rather than doing 20, we're going to do 10 with a standard deviation of 2, and we'll do a second one with a standard deviation of 2.236, and then this is going to be the sum of the two. It's not letting me double click because we have to delete these. Okay, bye. There we go. And we get the same answer. So even though the standard deviations, if you add them together, you get something much bigger than 3, right? 2 plus 2.36 is much bigger than 3. Standard deviations are not additive because there's some cancellation that occurs. When one is high, the other one is not likely to be high also. The standard deviation of the joint process is going to be higher, but not exactly double if you do two of the same thing. So rather than knowing all the probability ins and outs about adding normal distributed variables with different standard deviations and means, we just simulated 1,000 or 5,000 possible normal draws, found how long it took. This is how long it took in each of these simulated histories for our project, and then found how often we were done in 19 hours and used that as our probability. So the simulation is very powerful in that you can use simple rules to learn really valuable and interesting information. So when we come back, we will take a look at a waiting line application.